All right, guys.
You're laughing at her. She's
Hey, guys. So I've started. I don't know if anyone's sick today, but I've started the recording because we're going to start class.
Grant's not here.
Okay, so Grant, this one's for you. So, what do you notice about what we see up here? Obviously, they look like X's. Let's not point out like the super obvious. But mathematically, what do you notice is going on here? Robert?
well, for the third one, if you multiply numbers together, like if you multiply from each one, you know, like for x, because if you multiply that, you get x or something. It seems like an equation.
Okay, seems like an equation. Leon, you had your hand up next.
Okay, like all the numbers that aren't green, oh wait, I think they seem to add up to the center number.
Raider, what were you going to say?
Yeah, when you add up all the numbers,
Yeah, they do.
Yeah,
But I have another.
If we look at this as like legs and a center point, out of tissues over here. That center value is the sum of the legs of whatever we call this, the image that we see or the figure, whatever we want to say. So, do you think there's like a pattern here?
A change is going up by 4 each time from figure 0, which would just be nothing, goes up by 4 to figure 1, and then figure 1 to figure 2 is the difference of 8.
So if we had a figure 0, we'd be adding 4. But then you say you add 8. Okay, now I'm caught up with you.
And now you add 12 to get to 24.
Now we add 12.
And then you add 16, and then the next one would probably be.
This is a linear, I think.
You think 20?
Right.
Why would that be happening? What is it in this pattern that's making that happen? Greg?
I don't know, but isn't that linear? No, but the adding of the adding. That's like plus.
But that would make it quadratic.
Quadratic adding up.
That can't be linear because linear has to include.
If the change is the same, it's linear.
Yeah, that's right.
But if the change.
If the change in the change, so we look at the level 2, what we've called this before, the change in the change.
Yeah.
So the change in the change is 4 for each of those, but why? Raider?
Keep adding 4 new integers.
Okay, so we keep adding 4 new integers that are all the same because I'm going to put a new integer on every leg. But why is that first level change always increasing? Jacob, haven't heard from you yet.
Because, so, if you look at it from the beginning, so 1 plus 1 plus 1 plus 1 equals 4.
Yeah.
But then once you add the 2, it's basically like adding 4 again. But then there's another 4 added on top of that because it's basically just 1 plus 1 times 4.
Yeah.
And then for the next one you do 2 plus 1 because the last one was 2. And then multiply that by 4 again.
So if we tried to write a formula for this, like a function rule, we say that, I don't want green, sorry, we need red. We say that A is our term, N is our location. What term of the series or sequence or list or whatever you want to say. So N is the number of terms. So this would be A sub 1, this is A sub 2, A sub 3, A sub 4. So A sub N is at any given point. What would I do to get this? Leon, do you have a guess?
It'd be like n minus 1 times 4. It'd be like n times 4 plus n minus 1 times 4 plus
N
n
wait.
minus 2 times 4 and so on.
Okay, we want to try to simplify that down a little bit because that was a lot that you were saying.
Okay, so n times 4 plus n minus 1 in parentheses times 4, and then so on.
So you're saying the number of the term times 4 plus what?
And then
What does that get added to?
well, like,
The previous term, right? So we start to look at how we can talk about the previous term, a sub n minus 1. Because if I want the term before a sub n, it's a sub n minus 1. So if I'm at a sub 5, let's try this out. The next one would be a sub 5. That'd be 5 times 4 plus the previous value, which was 40, because a sub n minus 1 is a total of 40. Would that work out? Yeah. Do you know what it's called when we have a function that utilizes a previous value from that list? Mackenzie? Which one do you think it is? Huh? Our two names are explicit, not as in curse words. Explicit meaning like you know exactly what's going to happen. And the other one is recursive. If this uses a previous value, would that be explicit or recursive? Recursive, because I have to know what that previous value is in order to be able to solve this. You angry?
It says it right there.
I know, but you guys aren't always great readers. So this would be a recursive function because it uses a previous value to figure out the next value. If you want to see it done out with them, this is what you have on your paper. And then I don't know if it goes all the way. I try to save ink. Yeah, I try to not waste resources as much as possible. So I'm actually just going to skip on past this because it takes a minute to get to what I want to get to. So
In this problem, you will generate a sequence using an explicit...
I have this turned on so I can remember to turn that off because it's really loud in the video. So I apologize if you watch the videos and like the person comes on and talks and it's really loud. I'm going to try to leave it on so I can catch it and mute it.
Yeah, there's that. And then look.
So, a sequence is explicit when it doesn't use any previous value. All that we have to plug in is the number of the term. So explicit, you might want to make yourself a little note like off to the side. Explicit only uses the number of the term. And then obviously a coefficient or a multiplier to that. It can have constant values. It essentially is linear. Now, it won't necessarily be linear, but that's one way to think about it.
No, both of these involve curse words. Recursive has the word curse.
And explicit, yeah. So, if we want to find out the first 10 terms of this, easy thing to do, make a table, which is already done on your paper because we're going to do the got it on our own. Oh my gosh. So we set up a table and we list our term values. So I want term values 1 through 10, so I'm going to list out, okay, to find 1, I plug in a 1. To find a sub 2, I plug in a 2. To find a sub 3, I plug in a 3, and so on and so on. And we generate our list of values based off of that. So as they go, they get 6, 7, 8, 9, and 10. And what do we see about the change between each of these?
Okay, 3.
It's always plus 3. Why is that? Because that's my multiplier. I know that all my values are going to be multiplied by 3 times the term value. So whatever that coefficient is, it tells you what the relationship between the values are going to be. And this comes out to be linear. Because we see the change is consistent.
So now it's linear.
Any questions on how we did that? Try the got it on your own. We have a sub n. The function rule is 12 times n plus 3.
Can we make a table?
Yeah, that's exactly what we want to do. And really, once you know your first value, if you recognize that it's a linear function, it's really easy to fill out our table. So I make a table with n values. And then a sub n values, well, a sub n equals 12n plus 3. What would a sub 0 be? Let's just start there. 3, right? Then 1, and start working your table all the way up. So you should be doing this. You should make a table with, really just make a table with a couple values, but then we're going to jump to 12. So if I plug in, let's do 1, 2, 3, and then we'll jump to 12. So what would a sub 1 be then? What's that? 15. What would a sub 2 be then? 27. How can I do it without plugging the values into the function? Yeah, we just know everyone is going to add 12. So from my second term to my third, I can just add 12. So that's going to be 39. But now if I need to jump to a sub 12, just plug it in and do the work. 12 times 12 plus 3. What's 12 times 12? 144. So then this comes out to be 147. Any questions on how we do that? It should be pretty easy. We're just finding the output of a linear function right now, essentially. All right. So now when we move on to actually recognizing and writing out the rule, that gets a little bit harder. It's easy.
In this problem,
When we're given the rule, it's easy to find the values. But essentially now we're given the values and have to find the rule. So we can look at this a few different ways. We can say this one's 1, 3, 5, and sorry that these are kind of light on your paper. The copy did not pick up on them very well. How many are in this pyramid?
9,
Sorry, this is 6.
6, 10.
How many are here? 10, because we add 4 more on the bottom. 15, because we had 5 on the bottom. 21, because we had 6 on the bottom. So does this look like it's going to be linear? No, because my change is not consistent. So we can first analyze the change. Okay, plus 2, 3, 4, 5. Take a second. Don't flip your page. Take a second
Yeah, it works.
and think,
Yeah,
how is this telling me what to do? How? I have a plus 2, plus 3, plus 4, plus 5. I'm adding sequential integers. So how can I make a function rule to start this? Remember, a sub 1 is 1. A sub 0 we could assume is 0. I feel like I need to flip a coin.
I say Jacob because you already.
What do you want, Jacob? Heads or tails?
I say Jacob because you already
No.
chose Jacob.
Hey, rock, paper, scissors, lizard, Spock.
Roll a die.
I think you should
This
do
guy
it.
hides in.
Jacob, rock, paper, scissors.
Leon,
Oh, what? Oh, okay.
what were you going to say?
Oh, okay. I was going to say that, it seems to add the, like, so, the number of that term to the previous term.
To get to term 6, we added 6. To get to term 4, we added 4. To get to term 2, we had added 2. So what Leon's saying is any term, a sub n, that looks like a 9. A sub n, so what are you saying? A sub n would be the,
Current.
so how do I get it though? You said we're going to add,
The current term.
so we're going to add the current term value, so n will be added to.
A sub n minus 1.
Yeah, it's going to be added to the a sub n minus 1. So this would then be what kind? Recursive, because it uses the previous one. If you flip to the back, you can then see how we actually find that. And then where it says so dot 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 a sub n equals, we want to fill that in then.
Don't you need 2 equations to make it like actually recursive?
Yeah, it's
Don't
on the
I what?
bottom of the page.
You need.
Jacob, it's right here.
Yeah, I know.
Or are you asking about like these down here?
No, like you need two like functions to make it like recursive.
So, say more.
You need the sub 1 equals 1.
So, what do we know about a sub 1? A sub 1 is 1, right? So we also then want to say a1 equals 1. Is there anything else we need to classify? This gives me a starting off point. A sub 1 might be anything depending on the sequence, so we have to say what it is. Because then I could find a sub 2 or I could find a sub 3. So I have to not only list that a sub n is n plus the previous term, but I have to notate that a sub 1 is 1. We start at a value of 1. So that's why right above there, I should pull up your notes. Ah, my smartboard's slightly off. Give me a second. It's already listed for you, but we should highlight or underline or something. So thank you for pointing that out, since I just had it on the paper, but oh, it's up on the TV. I'm like, where the heck are you? Notice right here where it says a sub 1 equals 1, we have to talk about the fact that that is the starting point. The value of my first term is 1, and then we have to list both of these. So I would highlight or put a box around or somehow notate that that's special, it's important. A sub 1 is 1. I don't want ink tools, I want an ink layer. Questions on this? So now what if you're not given images, you're just given values? So, let me capture this real quick. So we have 1, 2, 6, 24. Write these out. Write these out a little wider from each other. 1, 2, 6, 24, 120, 720. Getting really big. Take a moment. Stop talking. Take a moment to just really think about how we could get from one term to the next. The hint that I give you on your paper is always look for simple, if we're getting bigger, look for simple addition that I can find a pattern with, or look for simple multiplication that I can find a pattern with. McKenna, I haven't heard from you today.
So to get the knowledge of the 3, you multiply by 2, and then each time you multiply by 1, 1, this times 3, times 4, 5, 6.
So how would we write that as a recursive sequence? Or a recursive function? So we always start, we gotta first list a sub n, well, whatever it is, here it's 1 again. Or, sorry, not a sub n, a sub 1. And then we want to say a sub n. Well, you just said we're multiplying by the term value. So it's going to be n times what? Yeah, because it's the previous term. It's a sub n minus 1. So this one, guys, you're being really rude. This one is the previous term value times the position of your new term. Yeah.
We could just do a sub n equals
Ooh, there's another one too. Yeah.
well,
Yeah, it's basically the same.
Yeah, we could list out like a sub n minus 1 and look at what it really is. Because, so how Leon got to this point is if we're looking at a sub, well, let's make it easy, a sub 4. So that's going to be 4 times, well, what was a sub n minus 1? A sub n minus 1, so a sub 3 is 3 times 2 times 1 because it's 6. So that's how, I don't know who made the jump first, but that's how they figured out, well, really, I could also list this as n factorial. Any questions on this?
Greg has officially.
I don't know if it's capturing or if it cleared or what it did.
Bye, Greg. Bye, Greg. It was a nice time.
It's their fault you're leaving.
Why can't you come back again? Mr. Hudson, we lost a student.
Yeah, it happens occasionally.
Do we have to fill out paperwork?
I'm going to avoid it.
Dad would need more paperwork.
Move on to the next section and check out our problem 3.
In this problem, you will write an
So now we need explicit. So now we cannot use a sub n minus 1. Explicit cannot use a sub n minus 1. So we have to figure out how I could write a function based off just what I see. So we start to look at a table of values, and I have a lot of this shown out on your notes. So we look at, okay, my first term is 1. My second term, I've added 2. My third term, I've added 3 to the previous term. But if we want to really talk about it in terms of some kind of multiplier involving term position with what we add in, how could we make this explicit? I shouldn't have filled in all this table for you. Like a sub 2, we have 1 plus the 2. A sub 3, we have 1 plus the 2 plus the 3. A sub 4, we have 1 plus the 2 plus the 3 plus the 4. And it just keeps going. But there's no function for addition like there is for multiplication. Like we have a factorial for multiplication. There's no function like that for addition. But think about this. Look at what they write out for a sub n. I really want you to take a second to see. A sub n is 1 plus 2 plus 3, and the dot 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 means there's a bunch of stuff in between here. Infinitely much. We don't know how much, but there's however much needs to be in between there to get us to our final term n, whatever the value of n is. I could flip that around and write it n plus the previous term plus the previous term to that plus all the way back to just plus 1. How does that help us? We know about combining functions.
Wait, so what how I looked at it is so I kind of looked ahead, but yeah. So what they did, I think, is they added the 1 to the n, and then they added the 2 to the n minus 1, and that's where they get the parenthesis n minus 1 part of it.
Have you guys ever heard of the Einstein Problem where his math teacher asked him to add up all the numbers from 1 to 1,000?
Did he do it?
He comes back in about, I think it's not, I don't know.
No, it's not. It's not. Or you
It's not Einstein.
Yeah, it was like Gauss.
What's the story? Wait,
Well,
what happened?
So, a famous mathematician, we can argue over who, but it's just a story that people like to tell. Who knows if it even actually happened? But so Leon said he thinks it's Gauss. Famous mathematician was in math class. Most really good mathematicians end up getting in trouble in school. Most really good students end up in trouble because they're bored. When kids are bored, they get in trouble. So this teacher, thinking, I need to kill a bunch of time with this kid, I will have him add up all the numbers from 1 to 1,000. He comes back in a very short amount of time. Says, got it, done. Here's your sum. It's perfect. His teacher, kind of perplexed, says, well, how were you able to do that? He said, well, it's easy. You asked me to add up 1 to 1,000, but if I think about doing it twice, I know that I'll have 1 plus 2, plus 3, plus so on and so forth, all the way up to 1,000. I can flip that around, but forget about the 1,000. The 1,000's not very nice. Only go to 9,900 or 999. Because then if I flip that addition around, what's 999 plus 1? 1,000. If I go down a term, 998 is also 1,000. If I go down another term, 997 plus 3, also 1,000, all the way back to that 1, which would also be 1,000. So he said if I did that, I'd end up with 1,000 thousands. But because I'm only doing this once, not twice, he just divided by 2 and found his answer very quickly. So it's all about thinking, how can I take something and make all the values add up to the same thing? So this next step that we perform here is exactly that problem, because what we're going to do is combine the two a sub n's. We're going to add these two functions together. So check this out. If I add my top function with my bottom function, I now am going to have 2 a sub n, because I have a sub n plus a sub n. So then I have 1 plus n. Okay, I get 1 plus n. Then I have 2 plus n minus 1, which gives me n plus 1. I have 3 plus n minus 2, gives me n plus 1. I have 4 plus n minus 3, and so on and so on. All of these sums come out to be n plus 1. But am I actually doing this twice? No, we're only really doing this once. So what would we want to do with this function? Okay.
So you know that there are n amount of n plus 1s because there are n like terms, I guess, inside of each function. And then you can just, so it simplifies to n times n plus, parenthesis n plus 1.
Yeah.
And then you divide by 2 on both sides.
So this is done out on your paper. If you look right here, you see the addition of the two functions. And then we come over here. So from down here, we really kind of come up to this like right column. Actually, we come from right here. I hate how the smartboard works with Word. Word is like the enemy to the smartboard because I need to do that. Okay, so this comes up to here on your notes. We see that 2 times a sub n, we have n amount of those values. So we cut this side in half, cut this side in half. We really have half of n times n plus 1. Do we have questions on how we got there? We looked at what would be the whole sequence. Then we turned it around, added them together to see that we find the same sums. And then we divided by 2. Do you want to do another one and then see if you still have a question? Try this guy. Except now we start with a 0. I'm going to see if I can fix this real quick. I forget how to make words. Actually, take a second. I need to make a PDF because this is just making me angry.
What is she doing?
So finding the 20th term would be really annoying here. So we add 3, then 5, then yeah.
Isn't that just like squares, but then you subtract 1?
Ooh. So Greg is thinking every time I'm going up like when my second level change is consistent, it's an indication of either quadratic or exponential, that sort of relationship. So Greg realized, think about the squares and take away 1. First term, 1 squared. What's 1 squared? 1, take away 1. 2 squared, take away 1. 3 squared, take away 1. 4 squared. So what, Greg, you're hypothesizing is a sub n equals n squared minus 1.
Yeah.
That's absolutely correct.
Yeah, good.
It's your fault you got it right.
So a sub 20 would be 20 squared minus 1.
Which isn't that like 399?
Yep, 399. Now, what if we didn't know? What if we didn't see that relationship? So let's imagine Greg wasn't in the class. We didn't have that jump to the right answer. Greg, our lives would not be complete without you. What?
Could be a giant.
I mean, we all love you, Greg.
What else could we do to solve this? Set up. Yeah, go ahead.
It's basically adding the next consecutive odd number to the previous term.
So when we think about this, when I add 3, that's like my first odd number, and then I move up by odd numbers. So really I'm moving up by 2 every time, 2 more than previously, right? So kind of we could say it's like my a sub n minus 1 plus, I know we need explicit, but plus n times, how could we even say this? So it would really be 2n plus 3 or something like that. But that's messy too, and we want explicit anyways.
Greg's formula.
We do the same thing that we did before. But instead of spending the time to write it out, just going to show it. Think about how we get the values. We started by adding 3, then we added 5, then we added 7, then we added 9. So we write out what we're doing. So to get this term, I'm really adding up 3, 5, 7. I'm really adding up 3, 5, 7, 9. I'm really adding up 3, 5, 7, 9, 11, or so on and so on, all the way up to my highest term. So then I again take both, like I take the list, and then I take the list flipped around, and I compare it. And really, what else it is?
Oh, it makes sense now. It was like a light bulb.
How what was the light bulb?
Like
Help us
when
out.
it flipped around, it took me a minute to realize like the flipped around aspect of it. Like how it adds up. I got it now.
How did they get the 2n minus 1? Does that work out too? Greg's squaring function worked.
Good question.
Yeah.
Will Greg's squaring method work every time? Like,
For that set of numbers, it will.
Yeah, for what we see there, it works.
But not for every set of numbers.
Let's see if their answer is the same. Boom.
no.
We end up deriving what Greg told us to.
Without all that stuff.
Well, but if we didn't see that, if we didn't recognize that they're all 1 below perfect squares, we'd have to do some kind of process like this. So I'm going to capture this, get it in the notes.
Basically, Greg just looked at it and he found it, so he didn't have to do the process. But
Yeah.
the process
How did you get to? Yeah, I'm known for finding the easy way out of things. Just stop.
The
It
way
was
you
so
said
like
it.
5 minutes ago.
Good. Good.
So think about, hey guys, can we stop with the extraneous conversation? I feel like I'm pretty understanding with you guys just kind of doing your own thing. You got to realize this stuff's tough and it's going to be tested. This is gonna be on those standardized tests that you're taking in like a month.
Okay.
This is term 1, term 2, term 3, term 4, term 5. What they're doing, this 2n minus 1 is the last value they add on, and because it's odd, if we multiply by 2 to the term value, that gets me the even number, but if I drop it down by 1, that gets me the odd value. So to go from 0 to 3, we added 3, right? So if I take 2 times the term number, well, 2 times term 2 gives me 4, but what did I actually add to get there? I added 3. So I take 1 away. What I add, it's kind of like looking at the recursive, but not using a sub n minus 1. So here, these are all the terms that we listed adding up to get there. So what we figured out is every term, the last number it adds on is 2 times the term value minus 1 to make it odd, because we recognized we had plus 3, plus 5, plus 7, plus 9. So think about it. Those are like your even integers. They're your odd integers as you go up. So to find odd integers, find your evens and take away 1. Or you can find your evens and add 1, but it would not work here, because then it'd be the next odd integer up, and that's not what we want. We want the odd integer below the even. So this 2n minus 1 comes from the last value added to get that term value. Because if I list out, like, let's think of a sub 6, since they don't go there. It'd be 0 plus 3 plus 5 plus 7 plus 9 plus 11 more, because here we stopped at 9. I can figure out that 11 based off it being the 6th term. 6 times 2 would give me 12. Take 1 away. 11's the last thing I need to add to it. So to go to the 7th term, what would be the last thing I add to it? 13, because I do 14 minus 1. To do the 8th term, I would do 16 minus 1, so I'd add 15 more. Whenever you see sequential anything, you can write a linear rule to make it work. I don't even know. Did I get? Yeah, I got that. Last thing we're dealing with today is using our formulas. So this is when we start to use our calculator. We do not have enough time for all of you to get out your calculators, but we're going to work through how you do it. If we begin with $300 on a credit card, and I am not, so this is one of the biggest dangers of the credit card. Pierre did not read the fine print. He did not read that the credit card was going to charge 1.8% interest each month to his unpaid balance and a penalty. Because normally if you don't pay the minimum balance, you pay a penalty. You have like a fee. But a lot of credit cards you can set up, pay my minimum balance every month at least. So Pierre ignored his credit card for 4 months. People do this a lot. They'll open up a store credit card and like buy a snowblower or buy a treadmill or something because they get a discount by opening a new card, but then they forget that they have that card because it's new and they forget to pay it off. So if Pierre forgot for 4 months, we want to set up a function to match this, and this is all in your notes. So we know it's going to be 1.8% more like added on to the original value. So that's where we get the 101, or sorry, not and, 101.8%, which really as a decimal value is 1.018. Anyone have an issue with how I got that 1.018? It was 1.8% more than 100. So 100% plus the 1.8, make it a decimal. That's going to multiply by your previous balance. A sub n minus 1 is your previous month's balance. And then the fee that they charge you is just a constant that gets added on. But this has to be for months beyond 1. Because that first month, we know that this previous, instead of using that previous, we just plug in 300. So then we work down. Why do you think we change our decimals here to having 2 places? What are we working with? Money. So in your menu, in the TI-83, if you just hit menu, you can get to where your decimal float just means it'll go as far as it needs to. Any other of these will round it at that location. So we tell it to round it 2 decimal places. And we can actually make our calculator do the recursive for me by using the answer button. So we first type in 300 to get that as my first value in the sequence. Then I want to multiply that every month by 101.8% because it's going to be what it was and an additional 1.8% and add on the fee of 29. Every time I hit enter, it goes to the next month because it keeps grabbing. This answer would now plug into here, and that's what gets you this value. Then that will plug in when you hit enter again and get you the next value, and it keeps going and going. So we will probably pick up tomorrow right here and then do 15.2. Your mastery for chapter 14 will be on Friday because I will have a sub. I got to take Marley to the vet. Homework would be good. Yeah, we did not name her. She already had her name. So, yeah, if it was up to me, because there's a movie about a Marley dog.
Marley died in the movie.
Every dog is going to die eventually.
Oh my gosh.
This was so mean.
Tons of dogs died.
Well, you have a dog.
You know what my view on dogs is? My job is to make my dog's life the best it possibly can be when it's sped up by 7 times. I mean, they age 7 times as fast as us, right? Jacob, where's your stuff? Please. This?
Oh, that reminds me